Hi, I'm Kyle Travis. I'm a petroleum engineer and an instructor for PetroSkills. I'm here today to talk to you about Completions and Workovers. Completions and Workovers is a one-week class taught by PetroSkills, and it's very well received in the industry. Today, I'm going to talk to you about acidization. And of course, completions, of course, stimulations are a big part of completions, and acid jobs are a big part of that. So let's get into the presentation. So these are a nice list of all our completion methodologies. Sometimes we underream wells, we'll intentionally create cavities in our formations. Even explosives have been tried, not very effectively. Matrix acidizing, very effective, particularly in carbonates, but also used in sandstones, and that's what we'll be talking about here in a little bit. Solvents, propped hydraulic fracturing. Of course, we frack a good many of our wells, most of our wells in the North America now onshore. We also acid frack our wells and occasionally pump chemical surfactant flushes to remove problems like water blocks and such. All right, if we're performing in a matrix acid job, we've got to keep our injection pressure below the frac parting pressure for the rock. It's absolutely imperative. Normally, our target formations for matrix acid jobs are higher perm reservoirs. We say greater than 40 millidarcies, but that's plus or minus. Carbonates in general are much simpler to clean up than sandstones, but we do perform matrix acid jobs in both. One of the things to be careful about with matrix acid jobs is using too much acid or too strong an acid. If we pump too much acid, we can dissolve the cement material in our formation and actually weaken it. In carbonates, that can lead to plastic flow or collapsed casing. In sandstones, it can lead to sand production and collapsed casing as well. So very detrimental if we pump too much acid. Other types of acid jobs besides matrix jobs include acid washes, where we pump acid and try to remove things like scale deposits. Acid soak. Acid soaks aren't used too much, but sometimes we perforate in acidic acid and perform a overpressured slow soak into the new perforations to clean up the perforations. Acid fracking is limited to carbonate formations only, in which case we are trying to create a stimulation in lower perm rock and carbonates. We've got different types of acids that we use in the oil field. We've got mineral acids like hydrochloric and hydrofluoric acid, which are very strong acids, react very quickly. We also use organic acids in our stimulations. Organic acids do not react as quickly as the mineral acids, and therefore have properties that make them very beneficial to use in higher temperature wells. And then hybrid acids are a combination of the two, both the organic and the mineral acids, and we get the beneficial properties of both. And sometimes we use retarded acids where we intentionally slow down the rate of reaction so that the unspent acid can get out further into the formation before it reacts. And then occasionally we use some solid acids, but we don't use those very often. Well, every acid has a dissociation constant, and that dissociation constant is an indicator of how fast that acid will react. And we've got acidic, formic, and hydrochloric acid here, and you can see that the hydrochloric acid has a dissociation content several orders of magnitude higher than formic and acidic acids, and indicating that it will react much faster, and it dissolves more rock than will the formic and acidic acid as well. So looking at our mineral acids, again, that's hydrochloric and hydrofluoric acid. Hydrochloric acid is used the most in the oil field. Typical concentrations go from 7.5% to 15%, but we can actually go as high as 28% concentrations. Hydrofluoric acid, HF acid, is normally pumped at low concentration, somewhere between 1 and 3% HF, and it's always pumped in combination with either hydrochloric acids or one of the organic acids. And those are normally pumped at concentrations of 6 to 12%. And we'll talk about why we pump those together. Again, generally speaking, these mineral acids are very powerful acids. They react very quickly, and there are certainly HSE concerns with them. If these acids were to get on your skin, they could burn a hole in your skin, and we have to be careful about that. Okay, this slide is addressing the strength of concentration of acid, because someone would undoubtedly say, well, why don't we always use 28%? Well, the stronger acid is not always the best acid. As I said in one of the early slides, sometimes if we pump too strong an acid or too much acid, we'll weaken the rock. If we dissolve the cementing material, we'll weaken the rock and actually hurt our well. But standard concentrations for HCl are 8, 15, and 28, with the most common 8 and 15%. The acid reaction in carbonate reservoirs, and by carbonate reservoirs, of course, we're talking about limestone and dolomites, it will dissolve the rock matrix completely, and that's very favorable. But if we have calcite cement present in our sandstones and we pump hydrochloric acid, it will dissolve that cementing material, weaken the formation, and again, lead to sand production and possible big-time problems. The reaction with hydrochloric acid and calcium carbonate is complete. Once the reaction completes, then all that's left is calcium chloride, water, both liquids, and CO2 gas. When we pump matrix acid jobs, particularly in limestones, limestones have a high degree of heterogeneity, and they oftentimes have very permeable streaks that run through them. So when we pump acid into those high perm streaks, they start eating away the formation and creating these holes. And the more acid that's pumped, the rounder they get, and we call them wormholes because they're fairly erratic, very similar to what an earthworm digs in the ground. So these wormholes can create highly permeable paths back to the wellbore, but if we keep pumping acid through there, we'll just keep re-stimulating the same rock. So sometimes we want to divert the flow of that acid, and we might do that mechanically with ball sealers, or we might do it with viscosity and gel the acid to cause more diversion and a more uniform dispersion of the acid. We pump hydrofluoric acid in our sandstones, okay? And so we call these treatments on sandstones mud acids. That's because they were developed to solve the problem with the damage that was being created by the bentonite back in the 40s when we were damaging our wells with bad drilling practices. We had a lot of mud damage, and so they developed the mud acid to dissolve the bentonite and clean that up. Well, HF, hydrofluoric acid, will react with calcium chloride, with calcium carbonate, with clay material, with silicate, which is what our sand grains are made of, and some of these reactions are positive, some of them are detrimental, particularly the reaction with calcium carbonate. When HF acid, that's hydrofluoric acid, reacts with calcium carbonate, it produces a damaging precipitate. And so we would like to avoid that reaction from occurring. The concentration of acids that we pump in these mud acid jobs can vary. The hydrofluoric concentration normally fluctuates between 1 and 3%, and then the hydrochloric concentration somewhere between 6 and 12%. Which particular percentages we use is a function of the clay content in the rock. This is all we have planned to present today regarding acidizing. In this section, we cover the organic acids as well. We talk about acid fracking. And this is part of the stimulation section. And of course, in the stimulation section, we also talk about fracking. I hope you enjoyed this and will join us for the next section, which will cover unconventional wells.